Cool. So hi, everyone. As mentioned, we're going to be giving a little bit of a tutorial on how to performance engineer your particularly LLVM-based programs. Now, this is intended very much to be an interactive talk. So if at any point you have questions or just want to dive into something, feel free to shout out in chat or just chime in, and then we'll talk more about things. Okay, so to begin, just a couple of general sort of setup recommendations, as well as places that are good to know about and things to do when you're trying to debug and generally interface with the LLVM community. So first of all, if you're building LLVM yourself, there's a couple of different ways that you might want to do so. The most common one that people tend to recommend nowadays is to build with assertions on. So then if there's anything wonky that goes within the LLVM compiler, you can sort of see that as well. But it's often that running a full debug build of LLVM can take quite some time to compile your actual programs as well as to compile LLVM. That said, there are cases where, if you're debugging, especially inside of the compiler, certain things, you need a debug build to see what's going on. In that case, you would want to go ahead and change your build type to a debug build, but oftentimes people tend to use this release and asserts as a trade-off. And if you're not getting quite into those weeds, then it's a good place to go, but be cognizant that depending on what you're doing, you might need a full debug build. More resources on compiling LLVM and getting that set up is available on the LLVM website. Okay, come on. For some reason it didn't skip the slides. Okay, so a couple of general recommendations, just if you're compiling a program to try out even before doing an intense sort of performance analysis. If you can generally use a fast linker, that'll make your compile times a lot faster. If you can turn on types of link time optimization, that'll allow you to do certain amounts of cross-module optimizations. That is generally a good thing to do if it doesn't dramatically impact your compile time. And Johannes will talk a little bit more about that at the end. Generally speaking, you almost always probably want to turn on optimizations when compiling code with LLVM. So the default when you were to just compile code regularly is 0. If you don't specify an optimization level, which is equivalent to no optimization. So double check quickly that you have actually enabled optimization. And generally also, it's useful to say that the architecture you're compiling for has all the different types of CPU features. So adding a -march equals native is a good default for the most cases. Also, often speaking, documentation on the LLVM and Clang websites as well as elsewhere, while not the greatest, has some more information, especially about different types of flags that you may want to use or different types of options that you may have there. If you want to do any sort of debugging, let alone performance debugging, turning on sanitizers is generally useful for this, and especially turning on debug information allows different types of tools to see where in your program certain things are happening. And again, as mentioned earlier, a release and asserts build version of LLVM is generally a good way to go. One other sort of broad thing, if at any point you run into particular types of problems or just have an interesting sort of thing that you think the broader community would like to discuss, there's a whole host of ways to get more involved in the LLVM community, as well as to interact and talk with people who might have even written the types of code that you're running across. We've now recently transitioned a lot more towards Discourse, which is a pseudo forum mailing list replacement. There's a Discord for more chat interactive sort of way of doing things. There's also IRC, which isn't persistent and tends to be a little bit older, so you'll get different sort of crowds of people who use LLVM on that. There's a variety of different sync ups and tech talks that the community has at large, which often feature a certain amount of time for people to ask questions, as well as some a new feature we have recently called office hours, where you can go and ask a supposed expert in certain types of the LLVM code base and community questions that you might have, and hopefully to be soon with Euro LLVM coming up, in-person meetups. I don't know why Google Slides does not actually click forward, but in any case, without any further ado, let's get into some specific ways you might want to performance debug your program. Yep, one question in the chat. Was the recording restarted? I think it was. At least something says it is.
Yes, it was.
Nice. Okay, so first, you've done all the primitive things that, made sure that optimizations were actually on, using something reasonable for your system, but your program is slow. How do we find it? And then how do we thus make it faster? So Something that I tend to use as a first tool is a performance analysis tool called perf. So it can take an existing binary, you can run it through perf, and then as a consequence, it will, excuse me, it'll be able to tell you where in your program seems to be taking a lot of time. Other approaches that people, excuse me, may have at first is to add printfs everywhere and to identify specifically, after this print, one second. Instead of adding prints everywhere, this will be able to tell you more concretely in the program where it actually is spending time. So first of all, it's able to provide hardware performance counters that tell you, hey, these are the types of instructions that I'm running. But more interestingly, it's also able to sample your program at various time intervals and see specifically where that time is being spent. Generally speaking, again, if you have your binary compiled with debug info, you can get some more specific source line information about where precisely in your program, rather than at an assembly level, you're getting certain amounts of time being spent. I specifically tend to use perf in a tool like this as follows. So first you run perf record, and then you have your binary and any actual flags at the command line that are needed to your binary. And this will go ahead and store a perf.data file, which says, based off of the sampling frequency, where in particular your program is spending time. I like adding this flag here, call graph equals FP, which specifies I don't just want to know the current call that you're inside of that is where I'm spending time, but specifically the whole backtrace. So then this allows me, for instance, to say, hey, I'm spending time in this function, but it's because it's being called a lot by these higher level functions. So we can see what this looks like in practice. So I can take that existing perf.data file that was auto-generated by that perf record, and I can run it through this additional command, perf report, that takes it and prints out, or rather has an interactive utility on the command line that shows you exactly where the time is being spent. So there's two types of percentage signs right here on the left, the first of which is children. So this is the total time taken by that function and all of its children, whereas self indicates this is the total amount of time of or percentage of the program that's spent inside of this function in particular, as opposed to any sub-functions called by it. So in this particular program, it looks like if we dive a little bit deeper into it, and we can, by clicking enter on top of the particular function after moving around, see the different calls that were being made by it. It looks like we're mostly inside of this Lagrange leapfrog function, and we're spending huge amounts of time in page fault. So we probably want to do a little bit of optimization with respect to memory. And as we sort of dive down the stack as well, we can see that some of the other large percentage of time being spent is again inside of page fault here. We can also then go ahead and inspect the individual sort of assembly level of any of these pieces of code, and we can see that individual assembly instruction is taking this percentage of the total runtime. So diving in a little bit more, again, most of the runtime actually was inside of page fault, but if we look at somewhere that isn't actually inside of page fault, we see that there's a large amount of time being spent on this particular floating point division here, as well as some move into what is presumably a spillover memory. Another important tool that people tend to like using, in addition to, of course, just adding prints everywhere, is to actually run the program through GDB. Now, while this is most common for just traditional debugging and trying to figure out why your program is having incorrect behavior, using GDB or LLVM is also incredibly useful for being able to debug why the performance is acting as such. So something you can imagine doing is you can take your program, attach it to GDB, which you can do as we have here at the bottom, where we start off a new run of the program, which goes inside of GDB, or if you have an existing program that's already running in the background, you can attach GDB to that currently running program where you get the process ID of it, and then you can specify that into GDB. Then again, if it's taking a really long time, possibly an infinite loop somewhere, you can pause the execution of the program within GDB, see the full stack trace and everything what's happening, as well as stepping through and trying to identify why whatever is occurring inside of your program seems to be taking a really long amount of time. GDB is also generally pretty useful because you can print out variables, you can specify exactly when you want to go next, or other sub commands, and more generally interactively inspect your program and see why it is occurring, or what parts in particular seem to be the parts that are very slow. So quick little mini tutorial on using GDP. Once we've run that earlier command, we can type R or run, and it'll start running the program. I can say do Control-C and pause the execution of the program, give it an interrupt that says we're stopping right here. You can alternatively also set breakpoints in your program that say, oh, I want to stop whenever you get to this, and then you can start running it. Once I've paused the execution, I can do a backtrace and say, hey, okay, I seem to now be spending most of my time inside of this particular calculate monotonic Q gradients for LLVM function, which itself is again called by all these pieces. And again, I can print out and potentially run any arbitrary code. So I can see, oh, I'm at iteration I equals, in this case, 115,674. I can not just print out, individual variables or registers, but I can in fact call arbitrary functions or other pieces of code, which again, if that piece of code is the part that's acting really, really slow, you might see your internal GDB printer hang a little bit there, but that's sufficiently useful to be able to identify, hey, this is indeed the part of the program that seems to be hanging or spending a really long time. Something also that, depending on what you're doing, might be especially useful is there's extensions to these tools. One specifically that I also tend to like using is a reversible version called RR, which in addition to letting you step forward in time and see how things play out going that direction, you can in fact also step backwards. So sort of similar to perf, in which you would first run the program and then get that perf.data that you can use to get the performance report. RR also allows you to first record the program that's run, and then you can, given that trace, step backwards or forwards in time and see exactly why certain types of executions are happening. So now that we seem to have a better notion of exactly where the program is being slow, let's now try to figure out why the program is being slow. And okay, there we go. Sometimes these problems, given that source line info, are relatively easy to fix, where you can go look at the source and say, oh, I have, say, an infinite loop here, or say even using GDB, I can identify, oh, there's this weird condition that I thought was being hit very infrequently, and thus I could cache and get away with good performance, but in fact it's not. Generally speaking, that should almost always be the first thing that you do, where you go back to your program and try to identify exactly, why algorithmically or at a high level that it appears to be spending a lot of time in those locations. But unfortunately, that might not always be sufficient to be able to identify exactly why your program is behaving as it is. This could be because, some optimizations you thought would apply are not actually applying, the most common of these being vectorization, which can give you, up to vector with potential improvement, or worst case, vector with level of slowdown where you would have anticipated it otherwise. But there's other types of optimizations as well, like loop invariant code motion or other types of hoisting that are very, very useful in practice that may have certain types of optimizations disabled if your program doesn't conform to the structure that LLVM's internal optimizer would expect. So something, again, without having to dive in super deep quite yet, that's very useful is using optimization remarks. And most optimization passes inside LLVM have some amount of optimization remark that provides feedback about why an individual optimization was not able to run. And again, the most common uses that people tend to have for this is determining why a particular program didn't vectorize or why a given location in a program didn't vectorize. So if we look at this code snippet here on the right, we can say, hey, it vectorized with cost blank, or it vectorized in this region, or potentially didn't vectorize in this region or not. And then you can use that information to try to assess, why it didn't vectorize, and trying to go ahead and fix that in your program to make sure it can vectorize. There's a ton of tooling across LLVM and Clang for doing this, and there's also a bunch of extensions that sort of allow you to do even more fine-grained or get even more info out of these internal optimization remarks within LLVM. Something else also that's very useful is there's this wonderful website called godbelt.org, or the Compiler Explorer, that lets you interactively write code and see the direct immediate impact of those operations, be it in the final assembly form, in the LLVM form, or whatever else. So I can go ahead and say, write this code F here on the right, and I can see from sort of like the source line info, where inside of an assembly program that would end up. And, if I'm getting the correct assembly instruction for my target that I would have wanted, or if I'm getting something that's subpar in that regard. So let's do a little bit of a dive in to using Godbolt, or and again, this doesn't actually need to be Godbolt. You can just run awk on your local machine, especially if you have a larger code base. But if it's a small snippet, using Godbolt is nice for just doing a quick little interactive bit. So you can look at the assembly, but I tend to first instead look at the LLVM IR itself. The reason being it's a slightly more high level, and it's also a lot easier to understand what a given optimization did or did not apply. So imagine we have this code here on the left that takes an input array, takes an output array, and says that the output is simply the square of the input. Now, it does vectorize, that's good, but there's still some weird performance here that when we go ahead and run it, isn't as fast, excuse me, in practice as we would have liked. So if we look at the LLVM for this, we see inside of there's this found conflict, which again, the name may not necessarily be there, but there's in essence a bounds check where it's looking whether or not that in variable and the out variable potentially overlap, because if they do overlap, you might not be able to vectorize as effectively because if you're writing and reading to the same location, you would get a different result. So quickly using that information, we can go and fix the problem by directly adding that information into our source code. In this case, we do so by adding the restrict keyword on both the input and the output. And if we look on the right-hand side here, we've now gotten rid of that extra check that has to see whether or not the input and the output overlap. However, there's still a little bit of extra checks here that would be nice if we didn't have to deal with. For instance, we can see here that it's first checking whether or not n, the size of this, is less than 4, which is presumably because it's vectorizing to a size of 4, as well as some extra fix-ups whether or not there's some overlapping iterations. Another technique in addition to specifying another technique that you can do in addition to specifying certain attributes at the source level, as well as just generally structuring your code, is Clang supports this special function called built-in assume, which propagates through to the LLVM level as an LLVM.assume, which means that the optimizer can take into account whatever high-level assumptions you might have and try to use that to optimize this code. So now again, using that built-in assume, we've gotten rid of that earlier check, which now goes directly into, in this case, just doing the trip count estimation. Cool. And without further ado, I will hand this off to Johannes to go into some extra cool pieces.
Okay, yeah, so let's pause for a second first. Do people have any questions for what we have seen so far? Maybe let's start there.
I have a question, comment. Would it be useful to show how you get the LLVM IR on Godbolt for those that haven't?
Yeah, we can do that. Let's take a step back. I need to reset the screen share really quick. I can open up Godbolt and a tab. Relatedly, we have inside of Godbolt that precise example right now, weirdly enough. Yeah, so specifically, you can specify here on the left whatever given input language that you'd like to use. You can also then specify for a or potentially multiple compilers how exactly you want to compile it. So for instance, we can start off with the default, which I believe is just say squaring a number. It by default runs it through GCC, and we have here the assembly generated by it. Of course, this is an LLVM tutorial, and we want to show the LLVM output of it. So it'll just take a second to shift on over to it. Here, Godbolt also happens to have an assertions build, which if you need that debug info, that should be built into this version, I believe. Again, as I mentioned, it's nice in being an interactive way of doing things. So if I want to just instantly here say, we're not just returning num squared, we return num, then the right-hand side here updates correspondingly. If you want to get that LLVM output from there, you would specify it by going and adding on the command line flags -s -emit -LLVM. So rather than staring at assembly, we can stare at the LLVM here. By default, you'll see this highlighting, which shows that this line from debug info of the source code ends up as the corresponding place here in the either assembly or LLVM. Depending on what you're doing, this additional highlighting can get a little bit of annoying or in the way. Sometimes it's incredibly useful and you definitely want it, but especially if you have a larger program. I often end up writing here -G0, which removes that debug info from right there. And also you can see directly that without any of those command line flags, again, unfortunately, the default when you run the compiler on a program is to run at the 0 optimization level, so with no additional optimizations. So you can see here, even for this simple program, there's a stack allocation being made, which loads and stores into it. Again, if we were just to add, in this case, just a simple optimization level like 01, then we have our code optimized nicely where there's no additional load store allocation. It just simply returns the input. Yeah, and you can also add additional windows. You can look at the output. You can even potentially execute your program on Godbolt. There's a lot of different tools, especially if you want to sort of do a diff to say, okay, if I run this at 02, I get this output. If I run it at 01, I get this output. That's really useful to sort of see side by side, which you can do inside of the Compiler Explorer website.
Excellent. We have a couple of more questions on the chat. One is, can you use private compiler?
So Godbolt has sort of internally a set of compilers that are built into it that it has and runs through, I think it's AWS technically infrastructure. So you can't as easily use a private compiler. You can, of course, make a pull request onto Godbolt itself, and then maybe they'll install it on the global machine. You can also take Godbolt, it's open source, and then run it on your own machine, and then use that to go ahead and see whether or not your private compiler on the nice GUI website. The other thing I'll just say is Godbolt is super useful, especially if you have like a small program and something very quick and dirty that you want to run on. But of course, if you have a large code base, or as the example you say, a private compiler, you can get the same behavior by just opening a terminal and running either clang or opt on that individual source file. Godbolt is nice in that it's interactive and on a website with some nice editors that you can go and see around, but all of this behavior is still equivalent to just taking the clang or opt or whatever else executable that you have and just running it inside of a terminal and looking at the output. So also, as was stated in there, another question is it possible to compile from multiple source files in Godbolt? Again, there are different ways for doing so. So it has special mechanisms for including from URLs. You can also alternatively run a command line flag on top of Clang. I think it's -E, which will just run the preprocessor. So any include files you have will sort of be like copy and pasted to output a single C or C++ code that you can again put right here. Might be a little bit unwieldy, but it is possible. But also the thing that I will say again, Godbolt, at least the way that I tend to use it, is super useful if you have like minimal examples or you're trying to put a bug report on LLVM. But if you have like a large performance engineering or like large project, it tends to be more useful to just run it through like the clang or opt on the system. So I don't need to do any of this makefile or whatever is so modifications since it's already right there. But use whatever tool makes sense to you for the amount of time it takes to set up and get the analyses you need. Cool. Another question in chat is, does it support intrinsics? Yeah, so any types of C++ intrinsics or C intrinsics that are available within Clang are also available here, basically because, again, the intrinsic support is inside of the compiler itself, not inside of the sort of like website extension to the compiler. So anything that the compiler should support should also be supported here. And again, if you're worried that there isn't a particular compiler or a fork of a compiler that has extra intrinsics already built into Godbolt, you can go ahead and just run that with a similar commands locally on your system. And yeah, as someone else in the chat also points out, the guy Godbolt, and yeah, this is actually the guy's last name is Godbolt, is really active in various Slacks. So if you find a bug report or like have a feature suggestion, he's very good about taking those. Cool. Any other questions on the other parts? Getting a link to the C++ Slack channel up. Someone's got it. Cool. Okay, I'm gonna give back the screen share to the part that Johannes was diving into. There we go, slide. Use slideshow. And screen share the slides back. There you go.
Perfect. Thank you. Okay, as before, please feel free to just unmute and ask questions, because this will be a lot of random thoughts that I will not go into detail of all of them. I'll just kind of summarize things. The slides will be available, so you can go back and look at different things, and hopefully you will discover one or two things that you haven't known before. If not, I'm sorry about that. Okay, let's dive into this. Let's try this out. Okay, so we heard before that LTO is a thing you should certainly look at. So LTO is link time optimizations, and the main idea is, by default, compilers optimize one source file, at least one translation unit, so like kind of one C or one C++ file at a time, for historical reasons mostly. And if you want to do cross-file optimizations, that ain't working. So in order to enable that, you have to, like, there's multiple ways to do it. Like, there is Unity builds. CMake has a feature that you can enable Unity builds through CMake, where it basically kind of copies all your files into a single one. That's kind of cool. And then the compilers come with LTO, which is link time optimizations, which does something similar. At the end of the day, if you use LLVM with LTO, what it does is, instead of building an object file, it embeds, or it puts LLVM IR into the object files. So the .o files are actually LLVM IR files. At link time, it links them all together, either into one big file, which is the default monolithic LTO mode, or it kind of only partially links them together, which is the thin LTO mode. So on both, you'll find information online. The thin LTO, you find a nice talk on YouTube that also explains the trade-offs and what you're winning. It's mostly about, compile time versus improvement. Profile guided optimization, especially if you use thin LTO, is kind of important. The compiler, the backend, inliner, and a couple of other places make use of profile information. So if they know certain loops are like executed a lot of times, so only a few times, if they know that certain branches are hot or like predictable, they will do different optimizations and hopefully better choices. So providing profile information is great. Obviously, it only makes sense if the profile information you generate is somewhat representative of your actual workload later on. Let's move on. So what I do if I'm kind of looking at a performance problem, I'm usually looking at the LLVM IR. Like, when I have a rough idea of where I'm looking, like where the problem is, I look at the LLVM IR and try to figure out if there is a clear thing that springs out at me. And after a while, if you've seen a couple of performance problems, there's things that you kind of see that they're weird or odd. To get LLVM IR, there's multiple ways. The one that I would recommend for various reasons is safetemps. Safetemps is great because if you do a compilation and you run it with safetemps, it will store basically the input to every stage of the compiler in a file locally on your system. And then you can inspect the input of every stage, and then you can also run the stage with that input in isolation. So in contrast to doing emit LLVM, you actually get slightly different output if you do safetemps. You also get different output if you emit IR under 03 versus under 00. And there is a lot of kind of nuances that are different. And sometimes most of the time they're not important. But if they are, you spend a lot of time trying to figure out what is wrong, only to realize at the end that the problem was that you looked at the wrong input. So safetemps pretty much gives you exactly what a normal compilation would use. So that gives you the most accurate, in my opinion, intermediate files that you can start your debugging session with. And then usually, if you have a big program, safetemps might be like the IR of the entire program might be too much to look at, and you want to narrow it down. LLVM extract is a cool tool to extract a couple of functions from a module into a separate one, such that you can work with them in isolation. It has a couple of shortcomings, and there's various options that you should take a look at, but it's certainly worth a look and good to know. Let's go to the next one. So one thing that I actually tend to like to do if I'm kind of missing an optimization. So I know this should be like this variable here, or this value should be a constant at the end of the day, or this loop should be removed, or something like that. The global should, we should actually not load the global anymore, because we should know what the value is. Anything where I'm kind of aware of the fact that something should happen, but it doesn't, what I usually do is I run the optimization pipeline multiple times, just as a quick check to verify that LLVM is capable of doing it. I mean, it's not a guarantee, but if you run, if you generate with safe temps the IR, and then you run O2 2 or 3 times on that, like one after another, and then you look at the result, and then the optimization you were looking for has been performed, you know that it's at least possible. If it hasn't been performed, you don't actually know anything. But if it has been performed, which often is the case, you know, okay, so it just didn't trigger if you run O2 one time. So that gives you kind of a nice data point, which costs basically nothing. Then if you have this IR and you optimize it multiple times, or run the passes manually, or even modify it by hand for all intents and purposes, you can also just use clang regularly to generate an executable or an object file out of it again, and in order to run tests like with perf and so on. So even if you go, you emit IR, you modify it either by hand, through opt, in any way, you can go back and generate an executable, so to actually see the real runtime of it. Let's go to the next one. When you're looking at crashes, it is often really helpful to try to bisect where something goes wrong. But it's also if you think that a certain transformation, a certain code, the way the code is written is somewhat bad, it might help to, or the performance drops at some point, it might help to use up bisect there as well. So up bisect basically limits the amount of passes that are run. So you can use there's extra scripts in the LLVM utils folder to use this to figure out which pass causes a crash, for example, or which pass does any other property that you can quantify after the fact. But it's really helpful to generate IR at a certain point. That said, there's also options that allow you to dump the IR if there was a crash. And there's options to dump the IR before or after an optimization pass, either only the IR that is affected by the optimization. So let's say it's a function pass, so it only dumps the function, or you can even dump the entire module before or after each optimization, which generates a lot of output, but sometimes still is kind of interesting to have, because then you can kind of just grab that model from the debug output and start with that as a starting point of your manual modifications, or bug point, or LLVM reduce to make a test case, and so on and so forth. Okay, let's move on. Then talking about passes, most of them have a flag to actually disable them inside of the pipeline. So you can kind of disable or enable certain passes that are run by default or not run by default through flags. But there's also a lot of options to modify the behavior of those passes. I mean, if you go with help on opt and clang, you see a subset of this, and then there's help hidden, which is way too much output usually, but at least it gives you an idea. Usually help hidden is really only useful if you grab for certain keywords that you're interested in. So you want to know all the options for GVN, grab for GVN in the input. Everything else is too much. And then, yeah, those flags it's sometimes useful to play around with them, especially there is a lot of thresholds and cutoff values. And sometimes you're kind of wondering why an optimization doesn't hit in your code. And it turns out that it just, above the threshold. So it has too many instructions in the basic block. And that is why the block was not looked at. Or there's too many blocks in a function. Or maybe the pass only looks at the first 500 stores, and the store you're looking at is store number 600. So it actually never looked at your store and tried to optimize it. So all these things happen, and all these things, we've actually discovered these in practice very recently. So right now, you don't really have good tooling for that part, but hopefully soonish there will also be tooling that helps you with these cutoff values and thresholds. Let's move on. Getting to the closing here, we have to. Okay, so now I have three slides of flags cheat sheets with some brief explanation. Obviously, if you do help and look at the Clang online documentation, you find a lot of other things that are useful there. But these are general flags in options for Clang and later opt that I use a lot, that help you to do optimizations, make sure you get the right target specific optimization and choices, work with floating points, vectorization, especially of math functions, deal with the opt-none issues and so on. Let's skip through them because the others are long and we're running out of time. This is about how to get optimization remarks. And here we have the source annotations and built-ins that are useful to do to actually improve your code and to give the compiler more information. And then if we go further, there is some research projects that you might want to take a look at, Bitospa, HTO, Oracle. There's some videos and some links there that show that you can add information into a program like these annotations and built-ins and so on and so forth, and actually gain performance. Funnily enough, you can also lose performance, which is not that surprising because the optimizations that compilers use have a cost model that is not necessarily related to the reality. But overall, you can kind of win performance. And these tools, some of them aim to help you gauge what the performance gap is. So there is a couple of tools already, and people should kind of invest more time in those because that really helps you to determine if you're actually losing out on things and if the compiler as it is can even do the things you want it to do if it had perfect information. And I think that was pretty much the end, right?
Yeah, I think that was the end. So
Okay.
yeah, if anyone has questions, please shout them out.
Absolutely. We have 5 minutes for questions, so feel free to bring up all your weird questions. Don't be shy.
I think we haven't asked us anything. Slide.
Guess we explain everything so well, nobody has questions.
Clearly. Well, if there aren't any questions you guys have immediately, again, as we sort of showed at the start here, there's a bunch of places where you can ask questions or ask about like weird performance debug info, be it the LLVM discourse, the LLVM Discord, various mailing lists, meetups, and so on.
David made a comment, question. There is no flag for opt to rerun the OX pipeline, maybe should be one. I mean, now the obvious answer, which I know you already know that is misleading, is opt has 0, 102 or 102 or 3, but they're not exactly the same pipelines, and you don't get exactly the same effect as if you run Clang 03. there is certainly a point to be made that one would like to replay the Clang 03 pipeline. I usually, if I need that, I actually go through Clang and the driver and just use IR as input.
The other thing that I'll say here is, like, again, if you're trying to rerun, say, OX multiple times, agreed, would be very useful to be able to run it multiple times inside opt. I'll typically just use a pipe to like take the output of a previous opt into another opt where I run 1, 2, or 3 again, and so on. Not necessarily a nice user experience right now, but if you need to do so, it is doable. And yeah, we should consider adding something for that.
Adding back on the comment that William made, can you tell us where you two are the most active? I know, for example, Johannes doesn't go that much into Discord, but some other people do.
Yeah, I think at this point, I tend to be a little more active on Discourse rather than Discord. Like, I'll be in a couple of specific channels there. I'm also a little bit old school, so if you respond to emails and or just showing up to some of the different like open design meetings for types of projects is a good way as well. Obviously, in some of the specific open design meetings, there's an agenda of things that need to be discussed in terms of like alias analysis problem X. But there's often time for someone to come in and say, hey, I had this problem. Other thing I'll add is, like, if you put things on like either Fabricator or GitHub issues, you'll often get a number of people who respond to me like, hey, this is weird. And however you are able to convey that information, tends to be some folks around who will try to help and respond.
Yeah, I mean, I'm personally on IRC most of the time, and I'm in I have one of those office hours every 2 weeks that people can show up in if they want. But Discourse and Discord should just be as like fine. Just go ahead and ask your questions every time, or a lot of times I see people reinvent the wheel or spending like immense amounts of time of doing things that could be simplified. And especially if you reinvent the wheel and you're not totally sure what you're doing, you usually miss out on corner cases that somebody could have helped you with and saved you a lot of time.
Which, to be clear, if you have like a cool idea and you want to go try your own stab at implementing X, either because you want to learn about it or because you have like a new different thing about it, totally go ahead. But you'd be surprised how many random and weird things there are already in the LLVM community. So if there is already something you can build off of or would immediately solve your problem without having to spend huge amounts of hours to go and build your own version of, generally a useful thing to know. Cool. And I think we're officially at time.
Thank you very much, guys. That was really, really good.